poštima.
Okay, tako? Super. Okay, lepo pozdravljeni. Hello everybody on the our invited talks for the ERK conference. Our first presenter is Luka Ambrožič from ELAF Propulsion Technologies. The title of his talk is The Evolution of the Electric Powertrain and the Potential for Future Vehicles, Trends and Introduction of the Distributed Drive Architecture. So please go ahead. I'm sure it will be a very interesting talk.
Hello everyone. Welcome from my side as well. I'll try to be very brief today. You've had a long day, so I understand everything. Everyone needs to get a beer or something. Maybe it's gonna get a little bit boring at times, just because I'm into this stuff and maybe you're not that much, so sometimes it's hard to get out of the hole. You know how it is with, you're all scientists, you're all in your specific fields, and I hope I can make it interesting for everyone, or at least help everyone to learn something new. It's gonna be a very broad presentation, more or less focused on giving you a sense of what's happening in the electric vehicle industry and in general in automotive, because I don't think there has been a more exciting time in this industry since the days of Henry Ford. So let's start off. What I'm gonna give you is a little bit of a background on the market, so how it's gonna look presumably in the next 20 years. Of course, it's gonna change 3 times, and you take a look at 5 different studies, they give you 5 different pictures, 5 different images of the future. But at least there's some trends that are clear. Where is innovation happening today? How does the powertrain fit into this, and how does it evolve and help the industry to innovate? How is the car going to look like in the future? And how we as a company, so I come from ELAF Propulsion Technologies, are trying to make things easier and better for other people. Right. Focus back here. Good. So I'm not sure if you know, but every year around the globe, there's about 100 million new vehicles sold, and passenger cars. And if you see today, or let's say in the recent years, there's about 1 to 1.2 billion cars on the planet every day. And this is growing rapidly. So don't think that something has changed. Every day we produce more cars, and every day people buy more cars. And the developing countries, as soon as they get some income, they're gonna buy even more cars. So it's a little bit of a different, let's say it's a little bit of a dilemma. You're trying to innovate to build better cars, different cars, but at the same time you want to grow. So you have to, these cars have to be sold, and you have to replace something. But on the other hand, you're trying to do something good for the planet, and you would ideally like more people to use a bicycle or walk. So you walk on thin ice, and hopefully, at least with our architectures, we can help to, let's say, rationalize vehicles and make them less daunting on the planet's resources. You can see that it's going to grow pretty much everywhere, and the majority of growth is coming from the developing market. Now, if you take a look at how this is distributed throughout geographies, you're going to see that more developed economies, where there is infrastructure, where there's a lot of bandwidth to absorb this kind of new technologies, is going to have a bigger share of these technologies. But otherwise, other technologies like internal combustion engine are still going to kind of drive a lot of the, let's say, consumption, or at least on the market, a lot of vehicles that are being sold. So if you look at this is supposed to be an image for until 2040. This gray area are electric vehicles, and this is the internal combustion engine. You can see that there is supposed to be a very quick phase out of this. I personally don't believe this can happen so fast. Even though the industry is able to innovate very quickly, it's quite impossible to understand. Even today, some places don't have electricity, and it's been around for so long that all of a sudden the infrastructure is going to get there. So electric vehicles, electric mobility, and in general, this mobility revolution is very much codependent on policies, on infrastructure, and much more so on the habits of people. So this is the hardest thing to change, is the habits of people. If you can do that, then everything would become more rational. However, usually you decide to build just more roads for more vehicles instead of changing the way people commute. And now where these trends are looking in is the car is basically changed. Whatever has been done in the last 100 years was only commoditizing specific parts and putting them together. Now we start all over again. You have to do lightweighting because obviously energy density, energy capacity is a lot lower with batteries and electric power than it is with a liter of gasoline. You have a lot of different architecture. Nobody knows what's going to be next. If someone tells you for sure, don't trust them. Nobody knows. Everyone is trying to find out. They're all experimenting. So every car, every electric vehicle that's on the road is actually an experiment. It's well tested, but it gives data. And everyone is trying to find common platforms so that they can do everything with the least amount of development cost and to get scale of parts. So, for example, one model of a vehicle today is built in 1 million pieces. That's very cheap for an OEM to produce, whereas an electric vehicle maybe sells 40,000 pieces, and each part is very expensive. This is a big problem, and those different OEMs, vehicle manufacturers, have gone into different ways how to approach these problems. And when it comes to electric vehicles, there's all sorts of other problems that you're trying to solve, and all come down to efficiency. Weight of the vehicle, its thermal performance of the vehicle, its longevity, so how long will things last, especially the batteries. How will you do the circular economy? How will you recycle materials, reuse materials, and all. And obviously, trying to figure out how you're going to grow on the existing platform. Now, when I say platform, this is basically very similar to saying a module. So you're trying to build things that make sense and that are scalable. Like I said, you need scale to achieve cost effectiveness. And the strategies are more or less cost versus performance. So if you want to sell a vehicle, it has to be impressive. But at the same time, if you want people to buy, it has to be cheap enough for people to buy. So what you're looking now is the second generation of EVs is becoming cheaper, but also nobody is pushing anymore for the huge acceleration. They're looking at top speeds of 160 kilometers per hour. They're looking at normal accelerations and all of this. And why it's really different is you cannot do it in the old way. There's not enough space in the vehicle if you build the vehicle in the old way. Just replacing the internal combustion engine and putting in an electric motor. You have to package things differently. You have to make sure that you have space for all the pumps, all the DC-DC converters, all the inverters, all of these things. Cooling, heating of the battery, cooling of the motors, power electronics, and a lot more. So it comes down to basically 3 areas. One is packaging of the battery and all the systems around it. Then you have to go through thermal management. There's a lot of losses in the system. How to size things. So internal space of the vehicle versus the external envelope. Why? I will tell you a little bit later. And the weight. And the most important thing is, like I said, nobody knows what's going to be next. Now, why does an electric motor in a vehicle make sense? It's pretty clear. Energy efficiency, it's the number of parts, it's the weight, and it's the simplicity. And also the performance. So you don't need to go to higher RPM to develop power, or at least torque. You got instant torque in most cases. You don't need very big multi-stage gearboxes, which are very complex. All of that makes it an ideal source of the mechanical power. Now, where does the energy come from? That's another debate, but let's leave that for now. Just as a quick example, you can see a typical combustion engine, just the motor and the gearbox powertrain, have 167 different moving parts. And I'm telling you, these are parts that move, that create friction, that wear out through time. And in an electric motor, it's a lot lower. For example, just the motor itself usually consists out of 3 parts. And probably 2 of those are just 2 different bearings. Anything else is usually magnetics. It doesn't wear out. Now, if we go forward, where does the efficiency come from? There's a lot to do of efficiency in a vehicle, but the majority comes from the weight of the vehicle and the aerodynamics. So it doesn't matter if you have a 99% efficient motor. Well, it does matter a little bit, but in the end, you're losing much more if you have 100 kilos more to push or to brake. And there's a big chain of all these things, and in the end, you're calculating the aerodynamic losses of the wheels themselves, of the brakes, and then you're trying to figure out where air goes to cool the brakes and all these things. So developing an electric vehicle has become a much more integrated task than it has been in the past, for example, by just combining different technologies. So you have a separate department developing the gearbox, a separate department developing the combustion engine. Here, multidisciplinary teams have to develop the whole vehicle together because everything is so interdependent. And as I said, you don't need the most efficient electric motor to have the most efficient electric vehicle. This is an important thing. You have to find out what works for the mission and for the user. So where are you trying to position the vehicle? What are you trying to give to the user? Where in the geography is the vehicle going to be used? Etc., etc. So that's the whole point of things. But you can see that just from the basics, you're already about 3 times better compared to the combustion engine. Now, mass is an important thing because where you are really changing things is the mass of the powertrain. If you imagine you have a central motor, you have some sort of a reduction gear, you have some sort of differential, transmissions to there, CV joints, half shafts. All friction elements all have to transfer power from one central part to a lot of adjacent distributed parts. It adds a lot of weight to the vehicle, a lot of parts, a lot of inefficiency. Now, remember before I told you that weight is one of the primary sources of inefficiency? Well, that's what people are doing today. So if you want performance, you have cars that are built out of full aluminum. If you want to have cost, aluminum is very expensive for vehicles. So what you're doing is you're trying to minimize everything in the car, make it lightweight so that you can make other parts heavier by using cheaper materials. It's always a play of cost, efficiency, and the sales price and everything that's very much interconnected. But again, this is being directly reinvested in lower cost materials. So material science, big part of automotive. Take a look at the cost of ownership of an electric vehicle versus an internal combustion engine vehicle. You replace 3 parts every couple of years. That's it. So it's a very big disruption to the value chain. After sales, aftermarket, as well as the production of it. And you can see that pretty much everyone is going to put out a lot of different battery electric vehicles, a lot of plug-in hybrids, simply because they will make the most sense. They need scale. So if they give out one model, not going to work. They need a lot to get scale to achieve cost effectiveness and make some money. So that's going to be a lot of a big push, and that's why combustion engines are also going out in the Western world. Now I'm going to go through really quickly because I know you don't have a lot of time. This is just a little bit of a background. So the powertrain architecture, this is the conventional mobility. You got a bunch of parts that have to transfer energy to the wheels. You got hybrid mobility, which is twice as complex because you're doing either a series hybrid or a parallel hybrid, meaning that you have basically two powertrains that you have to combine. A lot more expensive, a lot harder to package, a lot heavier, a lot more complex, a lot more moving parts. Temporary solution because, why? It can be built on the existing production lines into existing chassis, so you don't change the actual vehicle that you have in production. This is going from a single electric motor to multiple electric motors, at least one in the rear and one in the front. It's going towards one in the front and two in the rear. It's going towards one motor per wheel, and it's going towards motors directly into the wheel. I will show you some examples. This is just something that we've kind of sketched out, but the ideal in electric vehicles is a flat platform with a uniform weight distribution that allows you to have complete control over all of the degrees of freedom. You will understand this. So the vehicle only has 4 points of contact or 4 patches of contact with the ground. That's all that controls the vehicle. 4 tiny patches between the ground and the tire. And you want to be safely controlling that. Now the vehicle, when you move things outside towards the wheels, it's very similar to what our muscles are built like. So you have muscles directly in the joints where you're supposed to create torque. It's not a big muscle that's pulling all the strings on the arms and the limbs. So you're trying to do the same. Why? Because it's most energy efficient. You don't have losses in transmissions, but also because you have the best control. So what's happening today is every brand has its own platform, millions and millions of platforms. You've got Audi, you've got Volkswagen, Rivian, Faraday Future, Toyota, and a bunch of others. Toyota Prius, very simple electric motor and stuff. Toyota architectures. BMW, its own drive. BMW has made it their priority to build things on existing lines. So their electric vehicles are much like standard vehicles, but they also invested and sunk 8 billion euros into development of new materials, carbon fiber, polymer-based chassis, packaging, battery technologies, but they're not doing this anymore. Tesla has its own platform, Volkswagen its own platform, Audi, Daimler, Volvo, JLR. This is a fully aluminum car, I-Pace. Every brand has its own story, and they want to have control over what the user feels, what is the mission of the vehicle, and they all want to learn. The first platforms that are going to be used in the next 5 years are all focused on having control over the user story. Why this is important is because, as I said, Volkswagen is the people's car. Cheap, parts are cheap, huge volumes, nothing special but fits to the majority of the market. Mercedes is a very comfortable car. All these things have different profiles of the user. But is this going to be important in the future? Yes. However, it's going to be software defined. Doesn't matter how you will put things together mechanically, because you will be able to do this in software. And that's where modular platforms come in. You have one platform for a lot of vehicles. First, it's going to be within individual OEMs. Now, multiple OEMs are buying each other's platforms. And in the end, it's either going to be a standardized thing that anyone can build, or it's going to be a collaboration between. What's really more important is that today, there's so many ways to innovate. So a vehicle, an electric vehicle, has so many challenges that you can start from a lot of different opportunities and a lot of different fields. It goes from power electronics, silicon chips, networking, material science, efficiency of electric motors, gears, whatever, digital technologies, safety technologies, and even infrastructure. Everything ties back in together. And you have so much investment going into this as never before. And what this leads to is more motors per vehicle, scalable and modular platforms, data generation and learning is very important. China is fighting over data of its own vehicles, by the way, Tesla. Connectivity, edge computing, 5G, everything goes into the direction that you will be able to process data, send data, and make decisions based on this to make the vehicle suited for the user. And one most important thing I want you to remember is that when I say the word platform, it means two things. It's a bunch of hardware things, a bunch of parts put together, but it's also software. Platform today, a car, is digital as much as it is mechanical. So both of these things are very important, and that's where the future lies. Now I'm just going to give you a very short introduction about Elafe, and then I'm going to stop and let you do your thing. So scalable platforms, modular platforms, one motor per wheel platform. This is coming out next year. Rimac is already outside, same, one motor per wheel. And we have a very similar thing. Only we are able to achieve the same amount of performance as other people by not having any gears. No reduction gears, only the bearing, and we use the existing wheel bearing as the bearing of the motor. You can create the different top hats on the platform, very different ways, and it's vehicle size agnostic, and it's efficient, and it can actually mean that you have a cheaper vehicle in the end, because we save so much space and so much weight that you can make different design decisions on the car. Who are we? So Elafe at the moment, sorry, I wouldn't be in sales and marketing if I didn't say some good things about us. So I apologize ahead of time. I only have 2 slides about this. We're about 150 people working on design and development of powertrains. So everything together. Even we built even some prototype vehicles from the ground up, completely ourselves. This is our footprint in Ljubljana. We also have an office at Bransko and a laboratory for vehicle development, and we also have locations in China and in the US. And what we do is we create the platform for this, but we don't create the mechanical platform. We create the, let's say, the digital platform. We build the motors, but we also work on the software to control the motors. We also work on the software to control the vehicle, and we create it in a way that other people are able to innovate on top of it. So that means that we give other people benefits, and they can take advantage and make innovations. So we want to be an enabling technology for others. No more constraints on how the vehicle should look like. We're building something that is very related to an airplane, and we're building something that looks like a very boxy pickup truck. So a lot of different ways with the same type of technology. And you can, in the end, actually save in production cost a lot of money if you make the right design decision for the car. This is very important. These are just our motors, blah, 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 a lot of torque, a very small, tiny space, and lightweight. All the things that we develop ourselves in-house and all the testing. But I would just like to show you for the end what makes it really fun for us. And this is basically the ability to play around with the toys that we build, right? This is just an example of having a software-defined vehicle. Vehicle dynamics are now software controlled and updatable. You can pretty much do whatever you want with the car if the software tells you to do so. You can do a lot of different things by being able to control. We are 10 times faster than any ABS system stability control. We can turn wheels, we can generate torque positive or negative direction, which means that you can go a lot faster by having fun, or you can have a lot safer vehicle. Just as an example, if you see a deer in front of you, you have to swerve and get back around it. Now you have 1.8 seconds more time to make that turn. It could be a difference between life or death. So all these things help us, help others to make better vehicles. And that's where we are, and there's a lot of OEMs that are going this direction in the next years. So expect vehicles as early as next year, but some vehicles in 2027, 2028. And we have a lot of collaborations in the industry We work with Audi, with AVL, basically all the big companies in different projects. We build different types of motors in different types of vehicles. Testing, of course, a lot of other things. And that's it. I hope you enjoyed. I hope you learned something new. If not, maybe you have some questions that I would be happy to answer. Okay, next lecture. Good. Sorry? So every vehicle wheel has a bearing, right? So we use the same bearing. It doesn't make any differences because we have an outrunner motor, which means that the motor is spinning at the speed of the wheel. So basically, you just fix the stator onto the knuckle, and the rotor is fixed on the bearing. Use the same part that's already there. No, there is a bearing, yes. So, but that's the only moving part. So you don't have any other losses than the losses in the bearing. Everything else is more electrical in nature, not mechanical.
Yeah. So, congratulations. You've grown in a couple of years since I was listening to you in the classroom at the Faculty of Electrical Engineering. You have grown in numbers and, of course, in products. What is amazing to me is that a company like yours is still growing and not being sold, to be honest. So I'm wondering what is keeping you with all these big, companies around you.
Well, to be honest, we never wanted to sell out. We basically want to make a sustainable company out of this. One of the key things is also that the market is not very. So right now, if you were to sell, you're basically enabling the competition to shut you down. More or less, it would be more of a defensive move. But we are growing on account of understanding that this is becoming mainstream. So one of my greatest pleasures has been that we actually are self-sustainable and we create profit for us. So we're growing out of our own money. We have very interesting projects, and we get to do all of this from here, from Slovenia, which is way better than anywhere else. But there will be times where we will need influx of money, grow faster, because usually the problem is that there is a certain point in time where you have to react very quickly. That's when you need a lot of capital. It's a capital-intensive industry. I think those times are not very far away. Thank you.
Thank you, Luca, for your presentation. Now I'm inviting our next. Thank you. Keynote speaker. This is Dr. Szabo. He's I'm very proud. He's our visiting researcher at our Faculty of Electrical Engineering, University of Ljubljana, under supervision of Professor Damjan Miklaučić. Holds a PhD from Delft University of Technology. And the title of his talk is Influence of Electrokinetics and Electrostatics on DNA transport over length scale during gain electrotransfer.
Thank you for the introduction, and thank you also for giving me the opportunity to present my work. I'm here to talk about the influence of electrokinetics and electrostatics on DNA transport over length scales during gene electrotransfer. Now, there's a lot to unwrap here, but just for the start of the presentation, I want you to focus on gene electrotransfer and the other terms I'll introduce to you and as we go along the presentation. So gene electrotransfer is a technique in which you apply an electric field. When you apply an electric field, make the cell membrane permeable. And what this allows us to do is, it allows us to introduce foreign molecules into the cell. And depending on the electric field conditions, if they're mild enough, the membrane will reseal, and you'll get the molecule that you wanted to deliver inside of the cell. So this is electrotransfer, or it's also called as electroporation. And one of the primary purposes is to deliver foreign molecules into the cell. Now, how does this increase in membrane permeability take place? Why do we have cell membrane that's allowing foreign molecules to go inside in the presence of an electric field? So the cell is actually surrounded by a lipid bilayer. Here it's shown in a cartoon format, but this is how it actually looks. When you actually apply an electric field, one of the most accepted theories or says that you actually form pores or aqueous pathways or gateways for these molecules to actually go through them. That's how you increase the permeability of the membrane. And again, if the electric field conditions are mild, you'll regain the original state of the membrane as you saw over here, and you'll actually deliver foreign molecules into the cell. So this is, I'm deliberately using the term foreign molecules, but the talk is about gene electrotransfer. That means delivering a DNA or an RNA molecule into the cell through the permeable membrane. Now, why do we want to do this? Or why are people interested in delivering a DNA or an RNA molecule into the cell that's carrying a gene? One example that I'll use is, it's an unfortunate example, but it's also the best example to explain the process. You know, the current pandemic we are in, and you probably might have also, hopefully also been vaccinated. And you know, the companies Moderna, BioNTech, AstraZeneca have become household names. And the vaccine that they've actually got are nothing but delivery of this DNA or an RNA molecule into the cell. So this is one reason. It's to provide a therapeutic benefit. In this case, in the case of vaccines, it's to produce a spike protein, and that will produce antibodies against the virus. And fortunately, it works. Here you can see that the DNA on the RNA vaccines are producing neutralizing antibodies at least as much, or 4 to 8 times more, the number of antibodies that a person who's actually infected with the coronavirus is producing. Now, the point is that the DNA or an RNA molecule will not go inside. Even if you permeabilize the membrane, it's very hard for this DNA RNA molecule to go inside the cell. That's why, for example, Moderna or Pfizer, if you've got those vaccines, they're using lipid nanoparticles to actually push the DNA molecule inside. Or in case of AstraZeneca, they're using viral vectors to actually push the DNA molecule inside. So that's one reason why we want to deliver a DNA RNA molecule. There's also another reason, which is spinal muscular atrophy. It's instead of vaccine, now I'm talking about genetic disorders. So in spinal muscular atrophy, your nerves stop talking to your muscles. And when this happens, your muscles die out, they degenerate, they atrophy. And this is a condition that's usually found in children. And children who actually got this do not live to see their second or third birthday. So and one of the ways to actually cure this or provide some kind of therapeutic benefit is again to deliver the DNA or RNA molecule carrying that therapeutic gene. Because this happens, this lack of communication happens because a gene has gone defunct and the protein is not doing its job. So you can deliver a DNA RNA molecule with the correct gene and correct this protein. And why I wanted to actually introduce this is because 2 years back in Slovenia, there was a Go Help Chris campaign, where Chris was actually unfortunately diagnosed with spinal muscular atrophy. And the treatment which he actually received was Zolgensma by Novartis. It costed 2.3 million euros. And there was a fundraiser in Slovenia, and thanks to you all, the money was raised. And Chris is actually healthy now. He's going to kindergarten. So delivering an RNA or a DNA molecule has tremendous potential in curing diseases, and of course in vaccinating people, providing the therapeutic benefit that we hadn't seen before till now. But this is about gene transfer. I have still not introduced the term electrotransfer here. So I would like to take this opportunity to actually now introduce how electrical engineering, or probably an electric field is facilitating this gene transfer. So as I said, just to recap, lipid nanoparticles are pushing the DNA or RNA molecule, or viral vectors are pushing these DNA or RNA molecules. But now you also have an electric field that's allowing this DNA or an RNA molecule to go in. It works the same way. You have this jab. Instead of an intramuscular jab, it's now going into your skin. And you put an electrode on the skin, you deliver an electric field. And what it accomplishes is it delivers the DNA or an RNA molecule into the cell to produce the therapeutic antibodies that you would need. So this is gene electrotransfer. And Inovio is one company, but there are also European companies like Rotafarm or Takis Pharmaceuticals who are developing these vaccines. They are now in phase 2 or phase 3. So hopefully soon we'll also see DNA vaccines that are actually delivered using an electric field. Now, what we actually wanted to understand was how an electric field, this time an electric field, pushes or facilitates the delivery of this DNA RNA molecule into the cell. And in order to answer that question, we looked at 3 properties of the DNA molecule. You should understand that DNA is a very large, flexible molecule. So it will respond to external fields. It will respond to an electric field or a flow field. And one of the responses is that it stretches in the presence of these in this field because it's flexible. It's not just a small passive molecule. It's highly active. There's a lot of entropy associated with the DNA molecule. And it's not only flexible, highly negatively charged. And that's what we take the advantage of, or that's what the electric field takes the advantage of. Because it's negatively charged, it will react to the electric field. It will react by moving in the direction opposite to the electric field. And then there's another property which no one expected, but it's also coming into play, is collapse of the DNA molecule. The DNA, you can find the DNA in a solution and in a random coil configuration, but it can collapse or condense onto itself or onto other objects. So these are the 3 properties which we looked at to answer the question of how this goes into the membrane. So first, we had no idea of how a DNA molecule will actually stretch itself. So we conducted very simple experiments. We actually played around with the solutions or droplets of either water or DNA in it, and we bombarded them at microfluidic T junctions. This is a T junction, and the reason for doing this controlled experiment was to actually figure out the extensional viscosity, or the viscosity of the solution that DNA actually gives to the solution. And you can see that first I'll show you how a normal droplet actually breaks at the T junction, and as expected, there's a sudden snap off or a pinch off of the droplet. Snaps off suddenly, and this is expected. This is what we were also observing. But even if you add a tiny amount of DNA molecules, like in parts per million amount, you see a dramatic change in the breakup behavior. You see that instead of pinching off instantly, there's a neck that's formed that thins down slowly in time. And why does this happen when we add DNA molecules? So the reason was that DNA molecules respond to the flow field. They stretch. Just before the pinch off, you had the DNA molecules that were coiled, but as soon as the droplet was breaking, the DNA molecules suddenly stretched. And now what this stretching did was, so the capillary pressure actually wanted to pinch off the droplet, but there was nothing to resist it. But now with the DNA molecules stretch, there are elastic stresses in the solution that actually resist the pinch off. And that's why you get a very high extensional viscosity. So we had no idea how we can even stretch DNA molecules, but this was one of the control experiments which we could do and also observe the DNA molecules stretching. So now we actually said, okay, now we know stretching, enough playing around. Let's actually get down and do the actual work. Let's see how the DNA molecules goes inside the membrane. So one was stretching that we actually studied, and the other was, because now we are applying an electric field, the DNA will respond to the electric field and move in the direction opposite to it. So if you look at the problem of how a DNA molecule will cross the cell membrane, you can actually think of 2 possibilities. One, it's actually going in its native configuration, that's without stretching, without disturbing itself too much. Or if the membrane is too small, the pore in the membrane is too small, then it doesn't have enough room to go in its native configuration. It'll go in like a thread goes through a needle. That's how it'll go. So this has consequences depending on which is the pathway. So we wanted to figure out which one is the dominant pathway. But in order to do so, what we did was we varied the size of the DNA molecule. Because if you look at this mechanism, this is dependent on just electrophoresis of DNA molecule. And electrophoresis does not change with the size of the DNA molecule. So no matter if you vary the size in each experiment, you'll have the same loading efficiency or same delivery efficiency. But because in this case, the DNA has to stretch. That means there's a huge entropic barrier that the DNA must overcome. So in this case, the larger DNA molecule will have to stretch, unravel more, and it will create a lower efficiency for larger DNA molecules. So we did very simple experiments. We thought, okay, let's just vary the size of the DNA and see if the efficiency is constant. We have this mechanism that will probably be the dominant one. If the efficiency decreases, it should give us a hint that this is the mechanism of how a DNA molecule goes into the cell. So this is a sample experiment that I'm showing you for two different sizes. Here the DNA is actually in green. The vesicle or the cell membrane is in red. And when I apply the electric field, the DNA will actually go in the direction opposite to electric field, so it should go into the vesicle. So this was for the smallest size of DNA molecule. I don't know if the contrast is enough for you to actually figure out that there's DNA going inside, but I can show you for the larger DNA molecule, which probably has a better contrast, and you can actually see DNA is actually crossing the membrane and it's going inside. So this is for two different sizes of DNA that I'm showing you, but we did the experiments for different sizes and we saw that the efficiency was more or less constant. It didn't matter what size of the DNA was, it all went into the same efficiency. So we figured out that the dominant pathway is actually going in its native configuration. But there was a problem with these experiments. Now, we were able to test these experiments against models or theories. And the reason we were able to do it because this is a very simplistic model of cell or a cell membrane. It's nothing but just the membrane of the cell and a very simplistic membrane of the cell. Our problem was, can we actually extrapolate what we actually found over here to the case of an actual cell, where we actually want to do these experiments, where we actually want to figure out how a DNA goes inside? So perhaps not, because a cell, the vesicles that or the cell membrane models were actually way too simplistic. So we said, okay, let's also do in the actual cell, let's do the same experiment, keep the philosophy same, vary the size of the DNA molecule. So again, I'm going to show you two experiments. Now, instead of a vesicle, now you're seeing a cell over here. It's in a weird shape because cells like to attach to the surface and get attached to the substrate, and then they take all sorts of weird shapes. So that's why it's a in a funky shape, call it that. So here, here we applied the electric field, and the fluorescence that you're seeing is the DNA actually going inside the cell. Again, there's a direction associated to it. The electric field is from the right to the left, so DNA is going from the left to the right. This is for the smallest size of the DNA molecule we did. Again, philosophy is same, vary the size and look at the uptake. But now, we did for the larger size of the DNA molecule, and instead of having a direct access to the cell or DNA going inside the cell membrane, we saw that the DNA were forming aggregates on the cell membrane. They've condensed on the membrane instead of going directly inside. Now, this was not something new. This was already what was reported in the literature. This was kind of something new that we observed, but we weren't interested in what happens for small and what happens for large. Because we observed this difference, we figured out that in this case, for small DNA molecules, electrophoresis is dominating the transport. Whereas for large DNA molecules, we have electrostatics. The DNA is actually condensing on the membrane and forming these aggregates. So electrostatics is the dominant mode of transport across the cell membrane. And we wanted to figure out where is the transition. For small DNA molecules, electrophoresis, but for large DNA molecules, electrostatics. So there must be an intermediate size in between where we'll actually figure out where the mechanism shifts from electrophoresis dominant to electrostatics dominant. So again, I'm showing you cells. If you can make out, cells are actually the black shadows because they have nothing inside, that's why they are black. and the DNA is outside. Now I'm going to show you when we apply the electric field, for the largest size of the DNA molecule, we see aggregates, again, as expected. Now we are reducing the size of the DNA molecules, again, aggregates on the cell membrane. A little bit DNA is also going on. Further, aggregates still formed at an intermediate size. One can argue things are getting a little hazy over here. And for the smallest size, that's a 15 base pair, we didn't see any aggregates. If I can zoom in and show you better. So we figure out that the transition lies somewhere at around 25 base pairs, or it's base pair is actually a unit of the size of the DNA molecule. So if it's a term that you probably are not familiar with, you can think of it as the units we represent the size of the DNA in. It's the number of monomers of the DNA. So now we have these results. We have an electrostatic dominant mechanism to an electrophoresis dominant mechanism, and the switch happening somewhere at 25 base pairs. And we were intrigued. Why do we have a mechanism at 25 base pairs, or roughly around 25 base pair? Why is this the case? Do we have an explanation to it? We were able to actually explain these results based on Sagar's theory of condensation of DNA molecules. So what happens is, small DNA molecules are actually rod-like. They are not like a coil or a random cotton blob that you see here. They are rod-like. So below a certain size, for these rods, the DNA molecules and membranes enjoy various degrees of freedoms. They enjoy translational degrees of freedom and rotational degrees of freedom. And beyond a certain size, this is the isotropic state. Isotropic because they can orient in any direction. Beyond a certain size, if you increase the length of the rod, they prefer to align along their long axis. Now one can argue, why is this the case? Here the DNA is clearly enjoying more entropy. It has more degrees of freedom. It can rotate, it can translate. Here it can only translate. So why is this a spontaneous phase transition? Why is the DNA preferring to go from an isotropic to a nematic state at 25 base pair? And the reason for this is, as Sagar explained, was that even though there is a loss in rotational degrees of freedom, there is a much higher gain in translational degrees of freedom. So that's why when DNA is actually aligned beyond a certain length, it enjoys a very high entropy based on how it can slide along the long axis. So our results were actually consistent with the Sagar's theory, and that's one way we could actually understand or interpret our results on why we are getting this transition. So now I showed you results on two systems. One was the actual cell, where we are interested, where we got these results of electrophoresis and electrostatics being the dominant mechanism, and the simplistic vesicle models. The problem is that on cells, which is the reality, which is where we want to do the stuff, we cannot test models or theories. We cannot predict the uptake. We can observe and we can make inferences. On simplistic models, we can test theories, we can test experiments, but they are too simplistic. So is there a way to bridge the vesicle to the cell? Can we create slightly more realistic models where we can do the same experiments? And we decided to do that by adding a component of the cell into the vesicle. So here you have the vesicle, which is a cell membrane. The cell consists of all these other entities. We were only interested in one of the entities, which is the cytoplasm of the cell or the cytoskeleton of the cell. And we thought, can we add this and make more realistic vesicles? And the reason for doing that was because we had enough evidence that cytoplasm plays a dominant role in the transfer of DNA molecule across the membrane. Now, this was not easy because the vesicle that we formed here was using electroformation, and when you actually put proteins in electroformation, they denature. So it's not easy to just have an idea, okay, let's put cytoplasm in. It doesn't work as efficiently as possible. So we actually used microfluidics because in this case, we don't apply any electric field. We miniaturize the whole system, and we create these vesicles at a fairly high rate using microfluidics and using special solvents. So here you can see the same vesicles being created at a rate of 50 to 100 hertz with an excellent encapsulation efficiency as well. So because we were able to create these vesicles, we can put whatever we want in the inlet stream, and we'll get a very high encapsulation efficiency. Now, this was actually the work of our colleagues in the department, and then they actually figured out that you can actually form these vesicles in a solvent using microfluidics and the solvent will actually spontaneously bud off, giving you monodispersed vesicles. So here it's in slow motion. The lipids are, or the membrane components are in the fluorescent streams. You can put whatever you want here and you'll get them inside. And later downstream, you'll see that these octanol or these solvent droplets will bud off, leaving behind only the vesicle. So we were actually able to do this. We were actually able to put the cytoskeleton protein, and we were also able to control the encapsulation efficiency. We could put in a lower amount of one of the proteins, which is actin, or a higher amount. And we were also able to vary the salt, because the salt is needed to polymerize these proteins. Now, we had these more realistic cells, but in actual cells, this protein is actually not in the lumen of the vesicle. These proteins are actually attached to the membrane. And that's how they influence the gene transfer as well. The next step was, can we actually somehow attach these proteins to the membrane? And then we can add some agents such as polyethylene glycol, and then we could actually condense these proteins into bundles and also attach them to the membrane. So here you can see a micrograph which is showing that all the protein, instead of at the lumen or in the center, is now at the membrane. The only thing is it's bundled now. So now we had an intermediate system. It was extremely difficult to produce. It's also not very stable, as we were discussing as well. So, but now the aim is to actually do experiments on to test models of transport of how DNA molecule goes from the outside and the inside on more realistic systems instead of more simplistic. And then hopefully use these systems to actually predict the uptake of DNA molecules in the actual system. I don't know how much time I'm left with, probably not that much, but I'll probably like to wrap up as well at this point of time. So the question was how to deliver DNA into cell. That's using electric field. And in order to answer that question, we looked at three properties. First one is the electrophoresis, which dominates the transport for small DNA molecules. That's how the DNA molecules uses electrophoresis to go from the outside to the inside. For large DNA molecules, the DNA electrostatically condenses on the cell membrane, and the electrostatics then dominate the transport. And this is the transport over nanometer length scales, because the thickness of the membrane is just nanometers. So this is how electrostatics and electrophoresis actually dominates the transport over a very tiny length scale. Now we want to see if these properties, that's electrophoresis, electrostatics, and also the stretching of the DNA molecule, if these properties also help in transporting DNA molecules over larger distances in the tissue. So when you inject the DNA or any solution in your arm or skin or wherever, how will the DNA molecule respond to the electric field and migrate over larger distances using the same three properties? That was all for my presentation. And once again, I would like to thank you for the opportunity, and hopefully I've been able to interest you in the concept of gene delivery and how electric field actually relates to all of these. No, unfortunately, all the generators and the devices we used were commercially purchased. And that's one of the reasons I'm here as well, because we here have a lot more freedom on making these custom generators, and then a lot more control over what we are delivering. So for these experiments, it was all commercial generators that were commercially available. We didn't develop any electrodes.
For your presentation. Now we start with our second part. This is a celebration of 50 years of Slovenia Section, also 30 years of Electrotechnical and Computer Conference, started in 1992. under leadership of Professor Zajc. I'm very proud he's here. We'll invite you later. I'm thank you to all of you for that you are very patient with us, that you understand and help with our mistakes and what we are doing. I know it's not everything perfect, but so far the ERK is still alive. Every year there is still more than 100 people here, and I'm sure that we will continue for another 30 years at least. So using this opportunity, I will invite our Dean, Professor Gregor Dolinar, of Faculty of Electrical Engineering, who will also say some words to you.
Thank you, Andrei. So I'm very pleased that I can address you at this conference when we are celebrating also 50 years of Slovenian section of IEEE and 30th edition of ERK. Such a long tradition is not something which is completely obvious. At least two necessary conditions must be fulfilled, that's for sure. One is that the research area is very lively, and as we could hear today at this invited lectures, there are definitely topics which are very in the mainstream, what is interesting at this moment, and I'm sure a lot of other interesting topics will be discussed also tomorrow and in the future editions of ERK. Another condition which is definitely necessary to be fulfilled is that we have people who are devoted to this organization of this event. So there is a lot of work needed for organizing such an event, and I would like to thank really very much the people who are responsible that the ERK is alive for such a long time. Here we have Professor Zajc, here we have Professor Žemva, and a lot of others who are included in their teams and who made this event possible. So thank you to all of them, and I wish you a very fruitful day also tomorrow, and of course ERK will, as said by Andrei, definitely live also in the future years. So thank you to all.
Thank you. So now I'm giving the word to Andrei Trost. Share now this second part. And also helps a lot with organizing this conference.
Okay, sorry. So welcome in the name of IEEE Slovenia. I start again because we are transferring this via Zoom and YouTube. I will just shortly introduce the IEEE Slovenia section, which is one of the hundreds of sections of IEEE. We have members mostly from two biggest universities, University of Ljubljana and University of Maribor. And each year we gather at this conference, Electrotechnical and Computer Science Conference, here in a nice place at the coast, to meet to see what we achieved in the last year. And IEEE as organization is based on volunteers. We have volunteers that are leading the section, then volunteers that are chairing technical chapters and special interest groups, and we have 2 student branches. This year, IEEE Slovenia Section celebrates 50 years. In this anniversary celebration, we started with a welcome session. We will soon begin with an overview of the history of this session by Professor Baldomir Zajc. Then I will show a few recent activities and invite you to toast this celebration to all of you who are here in Portorož. But now I would like to invite a special guest from Region 8. Slovenia section is part of Region 8. This is Vincenzo Piuri, Region 8 Director-elect. He's joining us at teleconference at Zoom. So please, can you switch to Zoom?
Ladies and gentlemen, dear friends, good evening. Can you hear me? Can you hear me?
Yes, we can
good.
hear you.
I'm sorry, we're
Dear
just
friends,
waiting
no
for the sound.
We can hear you on the Zoom, but I don't know if they can hear you in the...
We can hear you now. Vincenzo, great to see you.
Okay. Let
Please
me
say
know
a few
when
words.
I can start.
Yes, please. Please, can you say a few words to our members?
Oh, yes, sure. Dear friends, good evening. As Director-elect of our Region 8 of the IEEE, it is really a great pleasure and an honor to participate in this event and celebrate with you the 50th anniversary of the Slovenia section. This is a great moment for the life of the section, for each and every volunteer, for everyone in the scientific and professional community in Slovenia and in our region. This is a great moment for the entire society. The continuous outstanding service of IEEE volunteers in Slovenia really made the difference, not only in the section, but in the entire Slovenia and the Region 8. Really, you have made the difference for humanity. We need to remember the past and celebrate the excellence, but we also need to build on the past, sitting on the shoulder of giants who have been fundamental for the scientific and technological development, as well as for the social and economic growth of the country. On their shoulder, we can see the future. Based on their knowledge and legacy, we can build our present and future, providing a better life for the future generation. Thank you. Really thank you from the bottom of my heart, from what you have done so far, and especially for what you will do in the future, for the Slovenia section, for the scientific and professional community, for everybody in Slovenia, and for the entire humanity. You can continue to make the difference and be extraordinary role models for the future generations. Be dedicated and caring. Continue to be responsible. Just be yourself. You are great. Thank you for what you will do. Thank you for being you. Congratulations again, and best wishes for all future endeavors. Thank you. Ciao.
Thank you, Vincenzo, very much for these words and for support of the region to our section. Now we will continue with the presentation of the history. So I invite Professor Baldomir Zajc to give us a talk.
Dear colleagues, now you will hear the story of Slovenia section during these 50 years. Why I am telling you? Probably I am the last person who is knowing the whole story from the beginning until now. Namely, from the beginning of the section, which was called at that time Yugoslavia section, through the years when I was at different positions, starting as secretary in Yugoslavia section, chairman of Yugoslavia section. Then I was in Region 8, regional conference coordinator, also regional director in 2005 and 6. That's why I'm here. I would ask you to read. I would ask you to read the text because I will not read these slides again. I will just comment the content on it. Before 1970, there were some contacts between our members and members in different countries where the sections were organized already. And so they see what are the benefits of sections to have. So Dr. Jože Furlan contacted Assistant Secretary of Regional Director. There were two main problems. First of it, there were not 50 members, what is the normal number to start, but Director Jaspers, he was, so I remember, from Université Leuven, Catholic Leuven from Belgium, ne? And he said it would be 50 members enough. And at that time it was a high problem to get foreign currencies, and also this is what they understood, and they opened a blocked custody account at Ljubljanska banka, so we were paying fees in dinars. It is obvious that interest of IEEE to start activity also in Eastern Europe was rather high. We were the first in this area. On June 21st, 71, RAP, this is Regional Activity Board in IEEE, approved the establishment of Yugoslavia section. This is the birthday of our roots. Then we had a section meeting, and the first chairman was Professor Miriam Gruden. After I wrote here also later were the chairman in Yugoslavia section, Jože Furlan, Mirko Vehovec, and since 88, also myself. We very early put the petition for the establishment of student branch at the session, and this was done, and we had from very beginning 2 branches, one in Maribor at university and one in Ljubljana, also at university. The official state registration, what is necessary in each country, was rather a problem, because at that time Yugoslavia organization, what is having adjective Yugoslavia, should be positioned in Belgrade. So we were hiding the session under umbrella of Elektrotehnička zveza Slovenije, Electrotechnical Association of Slovenia, and in Belgrade they were not against. In year 1984, President Richard Govan and Executive Director Eric Herz visited in Ljubljana, and they brought 3 medals to Rajko Tomović in Belgrade, Hrvoje Požar in Zagreb, and Lojze Vodovnik in Ljubljana. We got also a growth award because the members were higher and higher. Here you see we had already 300 members at the middle of 80s. In year 87, there was a regional meeting at Brdo, but before there were also one in Dubrovnik and one in Split. So Yugoslavia was, especially with this Adriatic, very attractive for such meetings. Here I listed also chapters at that time. This is signal processing, then is MTT and communication. These were the first 3. In year 1998, we put the candidacy to organize a Melecon conference. I will mention 2 conferences, Melecon and Eurocon. Eurocon a little later, but Melecon was running in this basin in Mediterranean area. This was in the year and in the time when in Maribor the army was marching already. So already we had 500 and more than 500 papers, half of the people there to come to Ljubljana. But the conference was anyway successful. We see that after 20 years, at the at the end of 80s, we had already around 700 members. But now, you know, we are at the time when each republic is having own plans and also own way and also own currency. We had at that time already dollar. That's why it was visible that this matter will never change and we will never able to integrate all republics together. At that time, I proposed 3 sections. One in Ljubljana, one in Zagreb, and one in Belgrade. Other areas, they didn't have enough members. At that time, the director of Region 8 was our friend Kurt Richter, who is sitting here. And he understood immediately the problem. So we went on April, at the end of April 92, to Graz. Namely, I proposed from Zagreb Szabo, Alexander Szabo, from Belgrade, George Paunovic. I will tell you also that George Paunovic passed away recently. So we agreed to propose 3 sections: Slovenia, Croatia, and the rest of Yugoslavia. I call this new Yugoslavia section. Instead of 20 years old Yugoslavia section. And RAP approved it. So on the roots of Yugoslavia section, we got 3 sections: Slovenia, Croatia, and Yugoslavia, the new. Later, in 96, when we celebrate 25 years, we all 3 got the banners like this one, but this is for 50 years. And it was obvious that all these decisions were also confirmed. What about Macedonia and Bosnia? So at that time they were not members, but later President Voli Rit went to Bulgaria and visited also Macedonia, and Bulgaria was proposed Macedonia, and they developed at that time the session in 2005. This is the 4th. But also in Bosnia, in Herzegovina, I made the mistake. So in Macedonia was in October 96, but in Bosnia and Herzegovina they got section in 2005. So out of old Yugoslavia section, we got 5 sections. And now we are at Slovenia section. Here is the birth of Slovenia section, August 92. To get that, we had to sign the petition. We have assembly to make also the state registration, what is not now here so much important. but it is important for history to be written the dates where we got it. Section chairman up to now, after me, Juri Tasic, Sasha Divjak, Andrej Žemva, Matej Zajc, Urban Urnik, and now Andrej Trost. This is also for library. I will not read all volunteers because they are more than they are here written, but at least some I put down on the paper. I mentioned before in Yugoslavia section 3 chapters, but we have now 2, 4, 6, 8, which are written here. We have still 2 branches in Ljubljana and Maribor, and also affinity groups. These are life members, young professionals, and women in engineering. Also, Slovenia section was officially registered, but the registration was not easier in Slovenia than before in Yugoslavia. It was a long procedure. I put here some awards, but there are more which I don't remember anymore. If somebody having still something can put here and that. But conferences. We are now at ERK, which is organized from 1992 for 30 years. The conference or conferences, they are giving the overview of the research activity in the country. They are forming bigger research teams for large international projects and is developing Slovenian technical language. Nobody else would do that. That's why we are very sensitive and we are still trying to. I could speak Slovenian, but in favor to Kurt, who was very much involved in our work, I am talking now English. He would like to talk that I would talk in German, but I have forgotten. Although as young student, I was working in Ruhrgebiet in Main Untertage, a year and a half, but I have forgotten German language. It is also very important, the Suter paper contest. But I will ask Andrej, in year 2016, I had the last numbers for invited papers, for normal papers, and for student papers. For next 5 years until now, I was just taking some numbers, so by feeling. If you want to have this strictly, then count how many was 2016, 2017, and so on, and add to those at 2016. This student paper contest is very much important also in Region 8, because we sent the winner, even probably 2 winners, one from branch in Maribor and one from Ljubljana. And in Region 8 is competition. During the years, our students got 4 first places, 5 second, and 1 third place till now. Since 2016, I don't know exactly, but I had 1 gold here already. The lady Brezochnik. This is ERK. Melecon I mentioned, so we were hosting Melecon in May 91, but I will mention also the conference Eurocon. Eurocon was in Region 8 the main conference, many years also the only. But then Jakob Barshem established Melecon for those Mediterranean basin, and in some celebration also African was established. But on the other hand, Eurocon had problem in 1992 or 1, and it was cancelled. After that, nobody wanted to hear, but I became the conference coordinator, and I was pushing slowly to return Eurocon, because at that time, all Eastern countries achieving the sessions and everything was changing in Europe, and I persuade them to allow and to accept that in 2001 new Eurocon started. We started in the center of Europe in Bratislava, but they were not very much experienced, and the conference was so-so, and they said, you see, it doesn't go. Then I asked them to give us, and Eurocon 2003 was in Ljubljana. It was running with ERK together in parallel, so all social events, all invited papers were for 1 or 2nd conference, and it was bigger, success bigger. And the success was growing. In 2005 was Belgrade, in 2007 was Warsaw, then I still know St. Petersburg, and recently I was reading a paper and I saw that in 2019 was in Novi Sad, so it is still running the conference. So I am at the end. I mentioned all what is here written. I was telling you already. So Region 8 committee had several meetings in Slovenia, before in Yugoslavia too, and now in Ljubljana. I know why. I didn't mention this recent committee meeting, which was in 2005. I mentioned just that one, 1988 or something like that. So there were several, and now I am finishing. Since, or better said, in last 10 years, I am not anymore involved in this business, so my English is also going down. So I apologize because I am forgetting, and I do not have experience, everyday experience in talking in English. I would one beer, what I can say.
So Professor Zajc, thank you very much for all you did for IEEE, for development of electrotechnics in our country and beyond.
It was all my pleasure.
Okay. So Professor mentioned that Kurt Richter is also here, and I'm pleased to give you to talk to us a few words.
Because, you know, words, but I could talk for 1 hour because of the experience Baldomir and I had. Because, well, I come back to your talk because I was the one who canceled Eurocon and you reanimated it. He was so angry, you can't believe it. Anyway, Mr. Chairman, colleagues, ladies and gentlemen, before I forward the congratulations from the IEEE Austria section, I would like to thank you all for the invitation to be here. I like Slovenia, I like Serbia, I like Croatia, because all these countries unique in the world. They celebrate the 50th anniversary twice. They celebrate the 25th anniversary twice, because last time, may I take this off because I was so happy that when I was invited a few years ago, anniversary here in Porto Roche, I never believed that I will come here. But then I saw the invitation. If this great, I thought. I know that I'm old, and in the age, the time is running fast, but I never knew that within 4 years, 50 years, 25 years are gone. Okay, anyway, so you are really unique, and I'm really happy to be here. Okay, on behalf of the chairman of the Austria section, who is not able to be here, I congratulate the Slovenia section to its 50th anniversary, and the chairman of my section wishes your section good luck and that it will prosper as it always did. Finally, please permit me to say a few words about the very difficult time the Slovenia section had, and I must say Yugoslavia had. Baldomir, you mentioned it. I was first as an Austria section chair. I was the founding chair of the Austria section, and I learned to know Furlan as the section chairman of Slovenia, but later on Baldomir, and since then we have a very good friendship, I believe. So I was at all the regional aid meetings you mentioned there. We were at the Eurocon 2000. Even I canceled it before. Okay. Anyway, I remember the Melicon in Ljubljana, because this was for Slovenia the most difficult time. I heard, fortunately later, that when I returned by train from Ljubljana and we stopped there for 1 hour or so in Maribor, I heard from the accident of the guy who died when he climbed on the tank of the Yugoslavian army then. This was exactly when I was there with the train. My wife was a little bit anxious when she heard about that too, but okay. everything went well. Anyway, then you didn't hear very much because there was the war, and suddenly I got a call from Slovenia. It was Bernardin. He said, listen, I was director. He said, it doesn't make sense anymore to have a Yugoslavia section because it breaks apart. And I propose, as he told, 3 sections. I said, okay. The first thing I asked, do you know who should be the section chairman? Yeah, I said, I have the names. It's Alexander Szabo in Zagreb and Paunovic in Belgrade. So I didn't know these guys anyway. And so we made the appointment in Graz, and believe me, I will make it very short. For me, it was not an easy decision. As a director of Region 8, as Baldomir later was too, you were director of Europe, Africa, Middle East, Near East, and Africa. And the decision to split a section in a country which is falling apart is not a technical decision, it's a political decision. And so I did a lot of thinking. If this is the right thing, shouldn't we wait a little bit longer or not? So finally, I decided yes, because in the headquarters in the United States, they needed my word so it can be changed. So these 3 guys came. It was not easy for Paunovic. He couldn't travel through Croatia at this time. He had to go via Hungary to Austria. But we met in the Milchmariandl. This is a guest house which doesn't exist anymore. And it was a very fruitful meeting, very interesting meeting. And finally, the Slovenia section was born. I was more or less the midwife for the Slovenia section and the also Croatian and Serbian section. Looking back, I believe nobody of us regrets this foundation of the new sections, and I wish you good luck for the future. Thank you very much.
Thank you very much. Now, you mentioned Alexander Szabo from Croatia section. I believe he's now on Zoom with us. So please, can you arrange that we hear Alexander?
Hello, can you hear me?
So, can you hear us?
Yes, I can hear you. Can you hear me?
Yes, very well. Welcome to say a few words to speak of how it was at the beginning of IEEE in this region.
Yeah, thank you. Thank you for the invitation. Dear friends, after the talk of Baldomir Zajc and Kurt Richter, I can not add much to that what they told us about the formation of the Yugoslav section and the 3 sections later. In 1975-71, the Yugoslav section was formed, and I would say that this happened thanks mostly to the volunteers in Slovenia. They have done a great job at that time, and I would like to thank you. And they can be proud that they were actually doing the job when the Yugoslav section was formed. We were very happy at that time that the IEEE section was formed in Yugoslavia, because we could join IEEE paying in our currency. It was a great problem for payment in foreign currency, and the formation and the arrangement with IEEE after this arrangement with IEEE, we could pay our membership fee in dinars, and this was the reason that actually the number of members was greater from year to year after the formation of the Yugoslavia section. I also would like to mention at this time Jože Furlan as the section secretary, who has done also a great job. He sent the information and invitation to join IEEE around Yugoslavia, and also his letters came to Croatia about the possibility of payment in our currency. I was actually not involved at the beginning of the formation, but I joined later the committee meetings in Ljubljana, because there were every year a committee meeting of the IEEE Yugoslavia section in Ljubljana. And the last meeting was in 1991, as Professor Richter told us. We were on the Melecon conference in Ljubljana, and all the members of the committee who were there met one day during the conference, and we were talking what is the future, what should we do, and we didn't know actually the answer. The conclusion was that we will wait and see what will happen in the next days, and then we will decide what to do. As a member of the IEEE, I was actually in Croatia, the man who was promoting IEEE. I was in contact very much with Jože Furlan. After this meeting in Ljubljana, Melecon in Ljubljana, actually the war in Yugoslavia escalated, and there was not the possibility to communicate, to travel, and now the most important role took over Baldomir, who told us about his contacts with Kurt Richter, and he also contacted me, and then we had this meeting in Graz. As we heard from Kurt Richter, we decided to make a division of the Yugoslav section into 3 sections. The Slovenia section, the Croatia section. In these countries we had enough members, more than 50. And then also in the, we actually then decided also to make the 3rd section, which consisted of Serbia, Bosnia-Herzegovina, and Montenegro and Macedonia. Although in 1992, Croatia was recognized as an independent country, and Bosnia-Herzegovina as well. But in Bosnia and Herzegovina, we didn't have enough members. So we had 3 sections. And then, as we heard from Baldomir, the Macedonia section was established, and later the Bosnia and Herzegovina section. So what was left over become the Serbia and Montenegro section. And this is the situation today. We have 3 sections. We have Slovenia, Croatia, and Serbia and Montenegro.
Okay, thank you, Alexander. We're running a little out of time.
Yeah. Okay, I would like to say at the end, thank you for inviting me, and I wish all the best to the Slovenia section and all the colleagues, the members of IEEE in Slovenia.
Thank you very much, and we wish you all the best too. You also celebrate this year, and
Yes.
Thank you for joining us.
You're welcome.
We have good relations with our neighbor sections, so we also received a short video welcome from the current chair of Croatia section. It's really short, so we can play it now. We're still on time.
Everyone, good evening, friends and colleagues from Slovenia section. My name is Ana Katalinic, and I would like to send our warmest regards on behalf of Croatia section in this short video message. I'm very sorry that I was not able to personally participate this evening in this great celebration. As you know, Croatia shares the same jubilee, the same 50th anniversary, and we all know the great role that we had in creation of Slovenian and Croatian sections, especially your own Baldomir Zajc and our own Alexander Szabo, who will hopefully join the evening virtually. It is a great opportunity that you made it to do it live, so I really hope that you will have a joyful evening, you will have a great time with your friends, and I really do hope that soon we will have an opportunity to meet in person. Just to end this brief message, something hopefully good in Slovenian. Želim vam srečno obletnico in prijaten večer. Upam, da se kmalu spet vidimo v živo. Hopefully this was okay. I wish you a really nice evening and hope to see you soon. Best wishes and best regards from Croatia, from Zagreb. Bye bye.
I have only this correct one? No. I have only a few slides to conclude. What we do in Slovenia section, our chapters organized distinguished lectures, either live or as online lectures, which can be also good for advancing the knowledge in electrical engineering. We organize seminars and workshops. We educate on all levels of education, do webinars. We organize excursions for our students, and we meet in the region. This is from the Students and Young Professionals Congress, and this is live members meeting in the region. Okay, they know that. Now, we compete, we give and receive awards to help our members gain interest in the electrical engineering and to advance in the field. Now, if you're not part of the IEEE, join us. If you're an IEEE member and not a volunteer, consider this, to join a team of people who's doing a great job. And now I want you to go outside to have a toast to our anniversary. Thank you.